Today we're discussing section 5.1 on inverse functions. So our objective is to determine if a function is one-to-one, and if it is, then it must have an inverse, so we find that inverse. Then we're also going to be working on simplifying these expressions, these compositions of a function with its inverse. So remember, from the very beginning of this course, we said a relation is a function if for every input there's exactly one output. So the following are not examples of functions. This first relation not being a function because the 2 repeats in the x place. Now this graph on the right is also not a function because it does not pass the vertical line test. It crosses the line at 2 places, so therefore it is not a function. So keep this in mind for today. To test if we have a function, we're using the vertical line test and no repeated inputs. Because now we're going to talk about inverses. You see, when we go from an output of a function back to its input, we get its inverse relation. So instead of giving an input and getting an output, what if I knew more about my outputs and wanted to know more about my inputs? That's when we start talking about inverses. And all we're doing here for any given relation to find its inverse is swapping our x and y. So notice, for this example, negative 8, 5 became 5, negative 8. And the same follows for each of these points here. We just flip the x and y. So now let's look what happens when we actually plot these points and plot their inverses. So first off, we have 2, 4. So that's a point right up here. Oh, the instructions say graph them in blue. Let's do this in blue. Here we go. 2, 4, negative 1, 3, negative 2, 0. Okay, there's the 3 points. Switching back to red. Now if I have if I have 2, 4, the inverse is 4, 2. The inverse to negative 1, 3 is 3, negative 1. And the inverse to negative 2, 0 is 0, negative 2. So let's plot those 3 points and see what we have. If I have 4, 2, I'm over here. If I have 3, negative 1, I'm down here. If I have 0, negative 2, I'm down here. So interestingly, all of these points have flipped actually directly over the line that goes right through here. Notice how they've all reflected perfectly over that line. That line is actually called y equals x. That's the line of y equals x. It goes perfectly through the origin with a slope of 1, and every time that we are finding an inverse, we're reflecting over this line. Now the same is actually true when we describe a relation using an equation. So given an equation, if we change the x and the y, then we actually get the inverse relation. So if we have something like y equals 2x, then the inverse is x equals 2y. So the blue line is our line y equals 2x, and the red line is our line x equals 2y, and that dashed line is our y equals x line. You can see how perfectly when we reflect the blue line over the dashed line, as in flip it over that line, we get the red line. And that's exactly what's happening with inverses. The one thing I'll mention is that on your homework, whenever you're asked for an inverse relation and not a function, you can enter questions like answers like this, x equals 2y. You don't have to simplify and solve for y. It's the first several problems that you have in your homework. On Pearson, you can actually just enter x equals 2y and things like that. No need to simplify, at least for the first couple. Now let's see a more complicated graph here. Remember, every time we want to find an inverse, we flip the x and y. And so something like negative 1, 6 becomes 6, negative 1. And then the rest of the table follows suit. Now, when you look at the graph, we go from something like this blue line, y equals x squared minus 5x. And when we flip it, it kind of turns on its side. And it becomes a parabola on its side, x equals y squared minus 5y. However, notice that the inverse now is not actually a function anymore. it doesn't pass our vertical line test. So more on that later, but that is something that we're going to have to be careful about. We want to make sure we're actually getting a function when we take the inverse. So let's see what it looks like if we don't immediately see what the inverse looks like. We're going to want to graph given the graph x equals y squared plus 1, graph the inverse relation, and hopefully the inverse relation is a function here. So we're going to start by picking up some points. So I notice I can pick up some very clean points here on the graph where I have 1, 0. I have 2, 1. And I have 2, -1. Which notice means it's not a function, but that's okay. For now, we're just talking about relations. So then I want to be able to pick up and write down, essentially, what is my function? What is my inverse function? Well, let's plot some of those points. The inverse points would be 0, 1, again, flipping the x and y, 1, 2, and -1, 2. So if I plot those points, 0, 1, 1, 2, -1, 2, then I get a parabola that looks kind of like this. And there it is, reflecting right over our line, y equals x, which cuts right through the middle like that. So that is our inverse relation. You do have a question like this on your homework as well. I highly recommend just writing down a couple of points, flipping your x and y, then you have 3 points to draw your new parabola. So what does it take to make sure that our function is going to have an inverse that is also a function? Well, what we're going to test for is called 1-to-1. So a function is 1-to-1 if different inputs means that we're going to have different outputs. So if we have something like f of a equals f of b, then it must be that the inputs were exactly the same. So it's kind of easier to see a non-example of 1-to-1. Let's suppose we have f of x equals x squared. Then when you think about f of -2, well, -2 squares to 4. And f of 2, well, 2 also squares to 4. So you have two things that map to 4, but -2 clearly does not equal 2. So this function, f of x equals x squared, is not 1-to-1. So graphically, we're going to use something called the horizontal line test. From the graph shown below, determine whether each function is 1-to-1 and thus has an inverse that is a function. So first off, we have the line 4 minus x. And you can see the red line is kind of playing as our horizontal line test. Essentially, hold your pencil horizontal and scan it up and down along the graph. If it only touches in one place, then it passes the horizontal line test. Right here, you can see it only crosses in one place horizontally anytime I move that red line up or down. And so this one is 1, 2, 1. Now, when we look at example B, you can see when I pull my horizontal line up along my graph, you can see that it is almost always crossing at two places. Here's a perfect example, -2, 4, and 2, 4. So this one is not 1, 2, 1. We have a couple more examples. Looking at this one, it's the cube root of x plus 2 plus 3. Holding our pencil horizontal, you can see it doesn't touch the function anywhere but one at a time. So this one is, in fact, 1-to-1. Lastly, we can see on our last function, this clearly crosses the graph in at least two places. It actually crosses in 3. Therefore, this function is clearly not 1-to-1. You can see it crosses here, here, and here. So that's a problem. 3 times is not okay. It's not 1-to-1. Okay, so let's suppose our function f is 1-to-1. Then the inverse of f also is a function. We write it f to the -1, and we read it f inverse. Now, This -1 is not a exponent, it's just a notation. It just means that this is the inverse function. So any function that is always increasing or always decreasing over its domain is a one-to-one function. That's one way to look at it. I like thinking about the horizontal line test easier. You guys all have graphing calculators you can use. So you can always look at the graph of a function and use the horizontal line test. You can also, though, look for if it's increasing or decreasing only over its domain. So just remember, in the -1 is not an exponent, and it is typically not the reciprocal. So typically to the -1st power means that we're taking a reciprocal of a number. That is also not the case here, because that -1 is not an exponent, just a notation. So you'll see it come up a lot. So if we say we're given a function f, we want to find f inverse. And so these are the steps to do that. We want to verify that f is one-to-one first. We want to relabel f with y just to make it a single variable. We're going to interchange our x and y, and then we're actually going to solve for y. Lastly, we're going to answer the question by giving it back with f inverse of x in place of y, and we're going to have the answer at that point. So let's walk through these steps in our next example. Determine whether the function f of x equals 2x minus 3 is one-to-one. If it is, find a formula for f inverse. So in order to find out if it's one-to-one, we want to see if it passes the horizontal line test. So to do that, let's look at its graph. Switching over to the graphing calculator here, let's go y equals 2x minus 3 graph. And you can see it is a straight line. And actually any straight line, so that there's no exponent on the x's, that is going to always pass our horizontal line test. Straight lines always have an inverse. So switching back to our example, this does pass the test. Excellent. So now we want to replace f of x with y. So we're going to say y equals 2x minus 3. Then we're going to swap our x and y. And we're going to be looking at x equals 2y minus 3. So we literally just use them as placeholders. Don't try to solve anything in this step yet. Just switch your variables first. Now we solve for y by adding 3 to both sides. Then we're going to divide by 2 on both sides. And we get y equals x plus 3 divided by 2. But of course, we don't want to give it in terms of y. We want to label it back as f inverse of x. So that's x plus 3 divided by 2. And there's our inverse function. That's exactly what it was asking for. So comparing these two, we're going to compare their graphs on the next page, but just looking at their tables, you could actually see how this comes out. If I plug in -1 into f, I get -5. If I plug -5 into my f inverse, I actually get back -1. Feel free to always test your work by plugging in a few points and seeing that your x's and y's are alternating. Now looking at the graph, you can also tell if we plot our two lines, then we see that our the two lines are perfectly being reflected over our y equals x line. So now when talking about our domains and ranges of inverse functions, they're actually not too bad to find them. See, the domain of f is always going to be the range of f inverse, and the range of f is always going to be the domain of f inverse. So this should feel kind of natural because our domain is our set of all x's of f, and the range is the set of all y's of f. Well, for this example, f inverse. Remember, we're flipping our x's and y's. So if I have an x in my domain of f, and I flip my x and y, well, hopefully now that y is in my range of f inverse. So as we're flipping x's and y's, the domain and ranges get flipped as well. So given our function f of x equals x plus 7 over x minus 5, find a formula for f inverse and determine the domain and range. So first we're going to check, is this function 1, 2, 1? And we're going to check this by looking at our graph. So going back to our calculator now, and we go to our y equals, and it is x plus 7, we got to use parentheses, x plus 7, close parentheses, divided by x minus 5. Again, make sure you use parentheses here. And if we look at the graph, okay, we want to check, does it pass the horizontal line test? And it does look like it to me. It'd be a little bit easier to check if we make our window a little bit bigger. So let's zoom out a little bit by going from minus 20 to 20, minus 20 to 20. Remember that this determines what is the all the tick marks on my x-axis and what are all the tick marks on my y-axis. Looking at the graph, see we've zoomed out a little bit. You can definitely tell that the bottom graph never intersects with the upper graph. And so we do in fact pass our horizontal line test. So we are good to go here. Back to our example. 1 to 1, yes. So now we want to find our formula. Well, let's label it y equals x plus 7 over x minus 5. And then we're going to swap x and y. And we get x equals y plus 7 over y minus 5. Now we multiply both sides by y minus 5. To undo the fraction, of course, I want to get rid of that as quickly as I can. And I get x parentheses y minus 5 equals y plus 7. Okay, well, now let's keep going. I'm just going to keep trying to combine like terms, distribute things, move terms around. Again, we're trying to get y alone. Let's keep that in mind here. First off, I'm going to distribute my x to both terms, and I get xy minus 5x equals y plus 7. Now I'm going to do some work to try to get all of my y terms to one side and non-y's to the other. So I'm going to add 5x to both sides. And then I have xy equals y plus 7 plus 5x. Now I'm going to subtract y from both sides, and I have xy minus y equals 7 plus 5x. Now here's at the point where I have all of my y terms on one side and non-y's on the other. Since everything on the left-hand side has a y, I can factor that y to the front and write y parentheses x minus 1 equals 7 plus 5x. So now I'm just one step away. I have y equals 7 plus 5x divided by x minus 1. And so there is my f inverse of x, 7 plus 5x divided by x minus 1. Now let me see, did I give myself more space? No. Before we move on, we do need to do the domain and range. So I'm going to have to write this over on the side. Let's talk about the domain of f first. Remember, the domain of f is everywhere where my denominator is non-zero. If I want to look at x minus 5 not equal to 0, I get x not equal to 5. So my domain of f is everywhere where x is not equal to 5. Now, of course, you normally want to write this in interval notation, but just to save some space, I'm going to leave it in this notation. Normally, you want to write it negative infinity to 5, union 5 to infinity, using parentheses everywhere, okay? So this is our domain of f. It's just everywhere where x does not equal 5, so we don't have a 0 denominator. Now looking at the domain of f inverse, and you'll see why I'm skipping range for a second. So the domain of f inverse is everywhere where x minus 1 is not equal to 0. So looking at my f inverse function, looking at its denominator is x minus 1. So I want x minus 1 non-equal to 0, and I get x does not equal 1. So this is x does not equal 1 as my domain of f inverse. Essentially, I can plug in all values where x does not equal 1. Well, then that makes the range of f really easy to find, because now I know the range of f is the same as the domain of f inverse. It comes from right there. It's x does not equal 1. Normally, we would have to look at the graph and try to pick up what our range looks like, something like that. But here, we just look at f inverse and say, oh, we know what the range of f is. It's the domain of f inverse. Similarly, we can write down the range of f inverse, and we know that's the same as the domain of f, which is x not equal to 5. So there's our domains and ranges. They become a little bit easier to pick up from the algebra here, going the two different directions. Okay, so what is so special about inverse functions and their composition? Well, what's interesting is if you plug a function f into its inverse, then you simplify. If it's truly the inverse, it will simplify all the way down to x. Now, x must be in the domain of f. This is not going to work for values that aren't in the domain. Don't, try to plug a negative into a square root function, things like that. But otherwise, it'll simplify all the way down to x. Also, if I plug f inverse into f, that will simplify all the way down to x as well. So let's see that in practice. So given that f of x equals 5x plus 8, and f inverse is x minus 8 over 5, let's check that these are in fact inverses. What we're going to do is find f of f inverse of x, and that's going to be 5 times x minus 8 over 5 plus 8. See, I've plugged f inverse in place of x in my function for f. Now, when I simplify this, the 5's cancel, and I have x minus 8 plus 8. Oh my goodness, 8. And of course, the minus 8 and the plus 8 cancel, and so we just have x as expected. So it worked in this direction. Now, you do always want to check that it works in the other direction as well. And we want to check that if I plug f in place of f inverse, that it simplifies also down to x. So I plug 5x plus 8 in place of f inverse, in place of the x. So I have a minus 8 divided by 5. So there you see I've plugged f into the x place. And so now I have a plus 8 and a minus 8, and I'm left with 5x over 5. And of course the 5's cancel, and I'm left with just x. So the inverse also works out this direction. It does need to work out both directions to check, but we have verified that f inverse is in fact the inverse of this function. Now, remember from the beginning when we looked at our y equals x squared example, and we realized that it doesn't pass the horizontal line test, therefore its inverse will not be a function. Well, what if we only looked at part of the domain? So for this example, what if we only looked at the part where x is greater than or equal to 0? That still has plenty of applications in the real world, so can we still say something about that? And yes, we can. In fact, if we do restrict the domain, several times we can actually get a function as its inverse. So for example, if I have y equals x squared all alone, just the full domain here essentially, and I look at its inverse, x equals y squared, well, that's not a function. But if I take y equals x squared and I restrict it to x greater than or equal to 0, so it's only the portion in here, then I can actually find its inverse. It's x equals y squared. It's actually y equals the square root of x when you solve for y here. And we do actually get an inverse function. We actually have that y will also be greater than or equal to 0. So super helpful to restrict the domain. We like to do this sometimes. How you might see it written is that if we take f of x equals x squared minus 2, you'll see that we're just taking x greater than or equal to 0. then you can know that it will have an inverse because we're not taking this part of the line, we're leaving that out. And so therefore, when you just look at this part, it has an inverse that goes like this. So there's another example, and this is the notation that you'll see it written as. You're given f of x, but then x is only greater than or equal to 0. That's when you know you're restricting your domain. So now for an example, given that f of x equals x to the 4 plus 1, looking at x greater than or equal to 0, determine if f is 1 to 1, and if it is, find a formula for the inverse. So if we look at our graph here, for this example, there we are, we go to y equals, and we're looking at x to the 4 plus 1. Make sure that you push the over button. Make sure that the plus 1 doesn't end up in the exponent with the x to the 4. So when we look at the graph, and notice we're kind of zoomed out, so let's fix our window, negative 10 to 10, negative 10 to 10, oops, 10. We look at the graph. Now, this is the full graph. There's not a great way to restrict the domain on your actual calculator. So what I want you to do is basically ignore the left-hand side of the graph and just look at the right-hand side. And you see how it's just increasing very rapidly on the right-hand side. So if we just consider the right-hand side of this graph, again, cutting it down the middle and throwing out the left-hand side, we do have something that is 1 to 1. So the answer to that first part here is yes, it is 1 to 1. Because, my slide went away. Let me get to the end. Back to where we were. There we go. And make sure my pen is on. And we're going to determine if f is 1 to 1. We said yes. It is 1 to 1. And if it is, then we need to find its inverse. So of course we label it y equals x to the 4 plus 1. We're going to flip our x and y. X equals y to the 4 plus 1. We're going to solve for y. Subtract 1 from both sides. X minus 1 equals y to the 4. Now we're going to take the 4th root of both sides. And we get y equals the 4th root of x minus 1. Now, the reason that the domain comes up, we kind of glazed over where that x greater than or equal to 0 plays a role. Remember when you take the 4th root of something, you actually get a plus or minus. However, we're only taking the positive half here, so we throw out the minus. And so this is its inverse. F inverse of x is the positive 4th root of x minus 1. And that's it. And so if you have any questions, please reach out. Use your calculator with these, look at the graphs, make sure you're looking for that reflection over y equals x, and you can have a ton of different ways to check your work here. So I highly, highly recommend it.